In section 1.2, we're going to begin discussing mathematical models and essentially just trying to recall this catalog of functions that we've already seen in an algebra pre-calculus course. And they're going to be important sort of going forward in when we get into calculus, these essential functions here. Maybe to motivate things a little bit, in this particular example, we have this table of data which shows the lifetime peptic ulcer rates per 100 population for various family incomes as reported by the National Health Interview Survey. So we can see that as the income level goes up, it appears that the rate of ulcer, or the ulcer rate, goes down. But can we be a little bit more concrete about this? Can we come up with an equation that would describe this specifically? And this is what we're going to try to be working up towards in this section. So here's kind of a scatter plot diagram. You may ask yourself, well, what equation would fit well, or would fit this data well? Or another example. Again, we have a table of data here. So the table below shows that the mean or average distances d of the planets from the sun, taking the unit of measurement to be the distance from the Earth to the sun, and their periods t, which is their time of revolution. So we have Mercury, Venus, Earth, and so on, all the way out to Neptune. They're measured in terms of Earth distances, and then t represents the period, which is how many times it takes for a revolution to occur. So we know the Earth, for example, is going to take 1 year to do to make a revolution. Whereas you can see that the further you go out, like towards Neptune, it takes a long time to make a full revolution, whereas Mercury is quite a bit shorter time. And here's a graph of the data set here. Okay, so why are we interested in, what are we interested in doing specifically here? So this is just one piece of the puzzle we're kind of fitting in. And so in examples 1 and 2, we'd like to find models or equations that describe the data as best as possible. The reason being, what we're going to be doing with mathematics is we're going to be presented with some real-world problem. We'd like to formulate or come up with a mathematical model or equation that describes that. From there, we can solve and do different things. Once we start learning about calculus, the derivative, integrals, and so on, we can do all kinds of stuff with that equation or mathematical model. And then from there, we begin to have mathematical conclusions. We can interpret that to make real-world predictions off of that, and then test to see if it makes sense. So this is kind of how this section sort of fits within the context of what it is that we're doing in trying to address these real-world problems. So we're trying to fit this piece of the puzzle, or we're trying to fill in this piece of the puzzle so that we can do all of the rest as we go throughout the semester here. And so these models, or these equations, can be constructed from the basic functions that we've seen so far in algebra, trigonometry, and pre-calculus, and that's what we're going to touch on right now. So the most basic function that we can talk about here is the linear function. With a linear function, it's going to be of the form ax plus b, with a and b being constants. So note that the domain is always going to be from minus infinity to infinity, regardless of the line. Well, I guess unless you had a vertical line, in which case you wouldn't have a function because it doesn't pass the vertical line test. Okay, so this is an example of a linear function. Right here. And there's not much else to say about this, other than, well, not only is the domain going to be from minus infinity to infinity, but the range is going to be that as well, unless you have a horizontal line. Okay, so let's generalize this idea. So we not only have these two terms here potentially, but we continue adding more and more terms like this until we have what's called a polynomial. So there's these constants, a0, a1, a2, all the way through an for each term. And in this case as well, just comparing with the linear function or linear model, its domain is also going to be from minus infinity to infinity. The special case is going to be the quadratic function, which has this form right here. And we know what this looks like. It's going to have this U shape where either the U is opening upward or it's opening downward. Now, if we increase the degree of this, the highest term, if the highest term is now 3 rather than 2, we have this cubic function, which looks like this, as another special case. If we have a 4th degree polynomial, the highest degree is 4, then notice it may have kind of this W shape, or it may even have kind of a U shape as well, depending on what your middle terms are. And then here's a 5th degree polynomial. Okay, so that's what polynomials look like. The next example of functions that we will often use as models are what are called power functions. And with these power functions, some of the functions that we've seen so far are actually examples of this. So with a power function, we just have x to the a, where a is a positive constant. Now, if a is 1, 2, 3, 4, 5, it takes these shapes, which we've already discussed, and it's basically a polynomial, a simple polynomial, a monomial, in fact. But we didn't say that the constant had to be a whole number, which we'll talk about here in a minute. But what are some of the trends that we can talk about as we increase these powers? Just talking about whole numbers anyways. Well, we can split these into two cases. So suppose the whole numbers that we're talking about are either even, like we have here on the left, or they're odd, which we have on the right. Now, in the case where it's even, the light blue one here is the original parabola. What happens when we go from 2 to 4? Well, 1, 1 stays fixed, as does minus 1, 1. 0, 0 also stays fixed. But what happens is the parabola is going to kind of flatten out near the 0 to the left and right. And then it's going to grow more rapidly once you get past 1, 1. And that trend continues if you go to x to the 6th, x to the 7th, or sorry, x to the 8th. It's going to increase more rapidly, and it's going to kind of flatten out more towards the 0. The same kind of trend applies over here if you're talking about odd degree power functions, where 0, 0 is fixed, 1, 1 is fixed, minus 1, minus 1 is fixed. But the higher you make the power, the more it's going to flatten out near the 0 to the left or right, and the more rapidly it's going to grow to the right. Now let's look at non-integer or non-whole number powers for our power function. Well, if we have x to the 1/2, recall that is, or sorry, the square root of x, recall, is x to the 1/2. Recall that the cube root of x is x to the 1/3 power that we learned back in algebra and pre-calculus. And this is what the square root function and the cube root function looks like. The reason we only have something on the right, and we're missing something on the left of the square root function is because you can't take the square root, for example, of -4 and get out a real number. We know what this is. This is going to give us 2i out, which is not a real number. So that's why you don't have anything here to the left. You can take cube roots of negative numbers, like -8, for example. The cube root of -8 is -2. That's because -2 to the 3rd power gives you -8. Whereas you can't come up with a real number, you have to use imaginary numbers. 2i squared, because this is a second root or a square root, would give you -4. You can't come up with a real number to do that. Okay, so these are what these root functions look like, and these are just examples of non-integer powers. So building off of polynomials in a slightly different way, rather than just focusing on one term and the monomial portion, and sort of building off this or taking in different directions, with a rational function, it's basically a polynomial divided by a polynomial. Its domain is very simple. It's going to be any real numbers x, and here I'm using the set builder notation, any real numbers x, the bar here means such that we have this condition, that the denominator is not 0. Very easy to find the domain then. So in these are two examples of rational functions. Its domain is easy to find because 1 over x is, its denominator is going to be 0 when x is 0. Here the denominator is 0 when x is going to be plus or minus 2. And so you end up having vertical asymptotes at those locations where the denominator could be 0. It's not always the case, but very often it's the case that you have vertical asymptotes there. We'll talk about when we get to towards the middle of the chapter some other things that you can run into with a rational function. Where might you see these things? Well, just in a basic chemistry class, Boyle's law is introduced. This is an example of a rational function to describe that relationship there, described in Boyle's law, where it says that V is equal to C over P. Or in other words, the volume and pressure of a gas, when you multiply them, give you a constant. So here's an example of a rational function. What if we wanted to determine the domain of this function? Well, this is actually really easy. All that you have to do is take the denominator, x squared minus 1, and see where it could potentially be 0. Well, that would be when x squared is 1, or when x is plus or minus 1. And looking at the graph, it makes sense that the domain is going to be everything but x equals plus or minus 1. So it's going to be everything but plus or minus 1. Now, the only other thing you have to look out for is you don't want the numerator to also be 0 at plus or minus 1, because then you won't have asymptotes there. You would have something different. You would end up having a hole. If the numerator and denominator are both 0 at the same x value. But in terms of answering the domain, if we're only interested in finding the domain, we don't even need to know what the graph looks like, and you can just do this condition. You can just see where the denominator would be 0. So what is the domain? We don't want this to be 0, so we don't want x to be plus or minus 1. Or in other words, all real numbers except plus or minus 1. Now, very often this textbook likes writing things in interval notation, so we're going to practice that. So this is what it would look like in interval notation. So we're just going from minus infinity to infinity, but we're skipping over plus or minus 1 and putting a union between the sets and the breaks here. Okay, so now we've seen rational functions. Another way we can kind of take polynomials and roots and some of the things that we've seen are into what are called algebraic functions. And what is an algebraic function? It is constructed using algebraic operations such as addition, subtraction, multiplication, division, and taking roots. Examples are the following here below. So x times the square root of x plus 3, the fourth root of x squared minus 25, or x to the 2/3 times x minus 2 squared. These are all examples of algebraic functions. Now, one specific example of an algebraic function comes from the theory of relativity, where it says that the mass of a particle with a velocity v is described by this equation, where c represents the speed of light, and m sub 0, or m naught, is the rest mass of the particle. Okay, so trigonometric functions. So in a trigonometry or pre-calculus class, this is where you would see this, or these functions. Now, you begin by talking about sine and cosine, which are periodic functions, which means that specifically every 2 pi they repeat. Here's their graphs below. Every 2 pi they repeat. Here's sine. So all that you need to do is know what sine looks like between 0 and 2 pi, and then it just replicates or repeats to the right and left in that same pattern. Cosine does the same thing. So just figure out what it looks like between 0 and 2 pi, and then it repeats. Now, they both have the same domain from minus infinity to infinity. They also have the range minus 1 to 1. And all the remaining trig functions are assembled from sine and cosine. So, for example, tangent of x is defined as sine of x over cosine of x. I'm not going to go into this in a lot of detail just simply because we're going to circle back around and touch on trig functions when we get into Appendix D coming up. So here's tangent that I was just talking about. It's defined as sine over cosine. Now, just like with the rational function we were talking about, there's going to be a problem if you're dividing by 0 here. So the domain is going to be all x values except for where cosine could potentially be 0. Where is cosine 0? Well, you can look at its graph and kind of see the pattern. Pi over 2, 3 pi over 2, 5 pi over 2, minus pi over 2, and so on. So here's what you get. The range is from minus infinity to infinity. Here's what the graph looks like. So just like over the rational function, when you're dividing by 0, that's going to introduce a vertical asymptote there at all of those locations. It turns out that tangent, it's 2 pi periodic still, but more specifically, it repeats every pi. Because notice right here, this portion right here, from minus pi over 2 to pi over 2 has length pi, and it repeats the left and right in that same pattern. So it is pi periodic instead of just 2 pi periodic. I mean, it's also 2 pi periodic, but again, more specifically, it's pi periodic. Okay, so where might you use trig functions? You should have already seen this in a pre-calc or trig class. There's lots and lots of applications for trig, but in terms of models, these periodic functions like sine and cosine are nice models for repetitive phenomena, such as tides, vibrating springs, and sound waves. So here's one such example. So the following model for the number of hours of daylight in Philadelphia T days after January 1st. And so here's a model for that involving sine. Okay, exponential functions. Let's talk about these. So exponential functions are the form a to the x, where a, the base, is a positive fixed constant. We don't want it to be 1, otherwise this isn't very interesting. It's just a constant function. Now it's going to look like one of two cases here. So if we had a number bigger than 1 for the base, like 2 to the x, then it's going to rapidly grow from left to right. The exponential function is one of the most rapidly growing functions. It grows faster than any polynomial, eventually. And we'll touch on that in more into like a Calc 2 class if you take that here at Olivet. If on the other hand you have a fractional number less than 1 as your base, then it's going to decrease rapidly from left to right. In both cases, the domain is minus infinity to infinity, and the range is from 0 to infinity. You can see that's common with both graphs. The log function is just simply an inverse function defined off of that exponential function. So we have an exponential function here in blue, a to the x. Recall the relationship between a function and its inverse. That if to go from the function and the inverse, you reflect over the line y equals x, which we have in green here. And that brings you to an inverse function, which we just define using this notation here. Log sub a, or base a, of x. Now, because the exponential function was so rapidly growing, if the base a is bigger than 1, the log function is going to be one of the most slowest growing functions. It grows even more slowly than this linear function, y equals x. What does y equals x do? For y equals x, you put in 2, you get out 2. You put in 20, you get out 20. And so on. The log grows more slowly than that. You put in 20, you get something out less than 20. Potentially far less than 20. So what happens as we change the base? As we change the base, if we go from base 2 to base 3 to base 5 and so on, it's going to grow even more slowly. Just simply because the exponential function on the other side was growing so rapidly. Now, we don't touch on the exponential and log functions the way that this textbook is laid out. We don't touch on them in Calc 1. It's not to the beginning of Calc 2 that we start touching on these in more detail outside of this section. Okay, so let's circle back around and touch on these examples that we use to motivate this section. So we're looking at the relationship between the income, the family income, and the ulcer rate. You can do a spatter. You can go ahead and do a scatter plot of the data, and here's what you get. The question we might ask is, what would we, how would we model? What curve would we use to model this of the curves that we've talked about? Well, it makes a lot of sense that it can be modeled with a linear function because it just looks like a straight line would nicely fit in here. If I can draw a straight line, let me see if I can do a little bit better. It's hard to draw on this tablet, make a straight line. Let me try one more time. Okay, that's not too terribly bad. So something like this. So we can see a straight line just nicely fits the data. It's not going to perfectly fit, but it's going to do a good job at accurately representing this data. Now, there is a procedure that can come up with a specific best fit line for doing this. This technique is called linear regression, or it's sometimes called a least squares line. So you can use just Microsoft Excel, Wolfram Alpha, or Desmos to be able to do that. And here's our other application. We were looking at the relationship between the distance and their period for all the planets in our solar system. And so here's what we have. Here's our scatter plot. What curve would we use to model this? Well, if we look, here's kind of the relationship that we have. And I went off track a little bit there. Let me try to do that again. There, that looks pretty good. This looks kind of like a polynomial or a power function that would model this well. The reason I'm saying it's a power function is just simply because it looks like it's going to start at the origin, whereas not all polynomials necessarily do start right at 0, 0, or the origin. Now, again, Microsoft Excel, Wolfram Alpha, or Desmos, those do nice jobs at, you can pick out the type of function. Once you've picked out that it's a power function that you want to model this, then you can find the best fit curve using what's called linear regression or least squares, but with a power function. And that's basically it for the section. We were just trying to get comfortable with a basic catalog of functions, linear, polynomial, power functions, and so on. And what is their range and domain? What do their graphs look like? What are some of their properties? And that's basically it. So go ahead and we've officially finished section 1.2. Go ahead and do all the WebAssign homework problems. I think you're ready for that.